In this video, we'll be taking a look at 2004 AB1 from the Form B test. And let R be the region enclosed by the graph of y equals square root of x minus 1, the vertical line x equals 10, and the x-axis. And so we have this graph here, and we're just looking for the area that's between the curve, the x-axis, and the vertical line x equals 10. So this one is just a straightforward integral from 1 to 10 of square root of x minus 1 dx. Now, even though this one could be done by hand, because it's a calculator question, it's still in your best interest to just use the calculator to solve the problem after you've set up the integral. So I'll bring up the calculator now. And we start with entering the function square root of x minus 1. And again, there are two ways we can do this. I'll show you both ways really quickly. We can go set up our window. Let's zoom standard here. And second calc option 7 for the integral, lower limit 1, upper limit 10. And you can get kind of a visual for what that integral looks like there. So it's the area under the curve, or between the curve and the x-axis, from 1 to the vertical line x equals 10. And it turns out to be 18. And the 000045 is just calculator rounding errors. Now another way that this could be done is if we go back to the home screen, we go to Math, and at the bottom of the list, near the bottom of the list, we have option 9, fnint. And since we already have the function typed into y1, we go to Variables, to Y Variables, Function y1, and you have to give the variable of integration, then the lower limit and the upper limit of integration. And you can see that we get similar, actually, not exactly the same answers, but this one looks even more accurate than the graphical one did. But this is for part A. We'll go on to part B now. All right, for part B, we want to revolve that area, which we call capital R, about the horizontal line y equals 3. So the horizontal line y equals 3 happens to intersect with this curve at x equals 10, and it would look something like that. So we're going to spin this around, and when we do spin this around the line y equals 3, it's going to produce a washer shape. And so the inside circle of the washer will be formed by spinning the curve square root of x minus 1. And the outside circle will be formed by, basically, it's spinning the x-axis around the line y equals 3. And that would look something like this. So when this is done, we're going to basically have a cylinder that is lying horizontally, and it has a bottom down at x equals 10. So if you looked at it from the right, past x equals 10, you'd just see a circle there. On the sides, you would see what looks like a cylinder, and then from the left, less than x equals 1, you would see that it is kind of it curves in. So we basically have a cylinder type shape there. Now you recall that the surface area for one of these washers is it's pi capital R squared minus pi little r squared. And that would give you the area. Then you recall that there is a small amount of height to it, or to give it volume. And that height to the washer would be a dx. So in our case here, the capital R, which is the radius of the outside, is going to be constant throughout, and that is just 3. So we would have that capital R is equal to 3, and little r is actually going to be 3 minus the height of the curve, which is 3 minus the square root of x minus 1. So for our formula and to set up the integral, we're going to have the integral, we can factor out the pi, the integral from 1 to 10 of capital R squared, which would just be 9 in this case, minus little r squared, which would be 3 minus the square root of x minus 1 quantity squared dx, and that's all we need to do at this point to set up the integral. You could simplify, but that would just be wasting time. All we have to do is to set up the integral properly and to use the calculator to find the answer. So we'll go on to that, to bring up the calculator now. So once again, we start with the function in y1, square root of x minus 1. Now all we need to do for this, or what we need to do for this, first of all, I'll turn that off by placing the cursor on the equal sign and hitting enter to toggle it off, is 3 minus, actually we'll need the pi in here, so it's pi times parentheses 9 minus open parentheses 3 minus, and because the function is in y1, we go to variables, y variables, function y1, close parentheses, square that quantity, close parentheses. So now we have pi times 9 and minus pi times 3 minus square root of x minus 1 quantity squared. So at this point, all we need to do is go back out. Our function that we want to integrate is in y2. If we go back out to the home screen and use second enter to call up the last command, all we really have to do here is change the y1 to be y2. Variables, y variables, function y2, and we run that and we get 212.058. And once again, that's all that we have to do for that particular part of the problem. We set up the integral and we use the calculator to find the answer. And so we will go on to part C at this point. Now for part C, we want to take the same area, and this time we want to revolve it around the vertical line x equals 10, which is already on our graph there. And so we're going to use, this time, cylindrical shells to accomplish this. And the cylindrical shells, we know the area is 2 pi r h, and in this case the height will be the height of the function, which is square root of x minus 1, and the radius, instead of being r this time, the radius, instead of being x this time, it's going to be a little bit different. Well, what x gives us is the distance from the edge, from 0, from the y-axis that is, up to the edge of the cylindrical shell. But that's not what we want. Then at 10 would give us the center of the cylindrical shell, and in between the area would, the radius rather, would be 10 minus x in this case. So that's what we're looking for. We're going to have a radius of 10 minus x and a height of square root of x minus 1. And when we go to put together our integral, we'll have integral from 1 to 10. We can bring out the 2 pi. The radius again is 10 minus x, and the height is square root of x minus 1. And a dx in this case is just the thickness of the cylindrical shell. So once again, that would look perhaps something like this. That's our thickness there, which is going to give us volume. And all we need to do is set that up, then we'll bring in the graphing calculator and find this. So we have the calculator open. y1 was our original function. y2 we used in part B. So rather than erase any of those, we'll go on to use y3 now. We need to start off with a 2 pi at the beginning with an open parentheses. Then I'll start another open parentheses for 10 minus x, close parentheses, then square root of x minus 1, close parentheses for the square root, close parentheses for that factor, and I think we still have one. We still need one more close parenthesis there. Yes. So that does it. And once again, all we're going to have to do now when we go back out to the home screen is to change the function name from y2 to y3. So go back out and do second enter to bring up the last fnint. So this becomes really convenient now. Variables, y variables, function, y3. Everything else stays the same. And hit enter. And this time we're going to get 407.150. And that does it for part C, and that does it for this whole problem here. So again, to reiterate, what we need to do is to set up the proper integral and then use the calculator to find the answer. We shouldn't use any calculator terminology or syntax as we're setting up the problem. We need to set it up mathematically and then use the calculator to just give us the answer. So that's going to do it for that particular part and for this whole problem.